Okay, well, good afternoon, everyone. Welcome to the CE 2310 review. I'm Barsha.
I'm Megan.
We're head tutors for this course. These are some of the topics that we'll be reviewing today. These should be topics that you've covered in class up until basically now. Beginning with transistors. Transistors are little electrical switches, right? They come in two types, P types and N types. P-type transistors are typically on when they receive a zero signal at the input terminal, which is your A terminal here. And P-types are also off when the signal at A is 1. N-types have the opposite behavior. They are off when your signal at A is 0. They are on when your signal at A is 1. This is an example of a type of transistor circuit that you'll typically have to work with on your exams. You'll be given just like a network of transistors and asked to figure out what the inputs at gate C and D are, at point C and D are, and then you'll be given all these intermediate inputs. The best way to work through these is just make yourself a little table with all the inputs and intermediate outputs. So you've got A, P, Q, C, R, U, B, S, T, and D. These are all just inputs I've pulled from the little transistor circuit over here. And then for an input, if A is 0 and B is 0, I'm going to put 0 over here, 0 over here. We're going to work through this circuit from left to right to assign values to each of your inputs. So for when A is 0, P is on, Q is an N-type, so it is off. The value at C is going to be 1 because you've got a switch that's, switch P that's turned on, so it just got a path from power. So the value at C is going to be 1. When C is 1, R over here is a P-type transistor, so it's going to be off, 0. U is an N-type, so it's going to be on because it's received the value of 1. Now your inputs, transistors S and T are connected to your B input here. So when B is 0, S is a P-type transistor, it's going to be on. T is an N-type, so it's going to be off, right? When you have like a series of transistors here, both of them need to be on in order to have a path to ground. These are both this is a parallel network of transistors, only one needs to be turned on in order to have a path to VDD. So because you've got path to power here, the value at D is going to be 1, right? I'm going to just populate this table over here just so I have track of all your values. 1, 0, C is 1, R is 0, U is 1, B is 0, S is 1, T is 0, and your resulting output at D is 1. Okay, I'm going to erase this so we can work on the next set of inputs for A and B. Now we're going to do A is 0 and B is 1. So you're going to follow the same way. So when A is 0, P is going to be 1, Q is going to be 0 because it's a P-type and an N-type. The resulting output at C is going to be 1. When C is 1, R is going to be 0 because it is a P-type. U is going to be 1. And then on this side of the circuit, you've got B is 1. So S, because it's a P-type, it's going to be 0. T is going to be 1. Now looking at this, you've got two switches in series that are both on. So there is a path to ground. And over here, you've got two switches that are off. There is no path to VDD. So your resulting output, D, is just going to be, is going to be 0. Because the value at ground is 0, the value of VDD is 1. Yeah? Okay, so I'm just going to populate this table here. 0, 1, 0, C is 1, R is 0, U is 1, B is 1, S is 0, T is 1, and D is 0. Okay, just going to erase all of these here so we can work on our third set of inputs, where A is 1, B is 0. So working through the same way, P is going to be 0 because your input A is 1, Q is 1. So the resulting output at C, is going to be 0. Because same way you did it over here, because you have a path to ground, your value at C is going to be 0. Because C is 0, R is going to be on. It is a P-type that is activated or active high when your input is 0. U is going to be 0 because it's an N-type. Working from this side, when B is 0, S is going to be on or 1. T is going to be off or 0. Now, when both of these are 0, these both are open switches. There is no path to ground. These both parallel transistors, there is a path to power. So your resulting D output is going to be 1. Right? Okay, I'm going to populate my table here. Got 1, 0, 1, C is 0, 1, B is 0, B is 0, 1, 0, and 1. Okay, and then for our last set of inputs, I'll erase this table here. In the green, you've got A is 1 and B is 1. So again, working from left to right, when A is 1, P is 0, Q is 1. So C is going to be 0 because there is a path directly to ground. When C is 0, R is 1, U is 0. When B is 1, S is 0, T is 1. So you've got a similar situation where you don't have a full connection to ground, but in this parallel circuit up here, you have a connection to power through the switch. So the value at D is going to be 1. Okay, so I'm just going to write this table here. It's 1, 0, 1, 0. R is 1, U is 0, B is 1, S is 0, T is 1, and D is 1. So you've worked through all of your inputs A and B here. I'm just going to fill in this table based on the values you've already come up with. So C is 1, 1, 0, 0. D is 1, 0, 1, and 1. And that is your completed truth table for this particular circuit. Okay, any questions? Okay, I'll scroll down to our second topic, which is logic gates. These 3 gates are things that you should be familiar with. The first on the left is your AND gate, OR gate, followed by the NOT gate. The key is when you have an AND gate, like 2 inputs are ANDed together, the output is going to be 1 only when both inputs are 1. The OR gate output is going to be 0 when both inputs are 0, 1 otherwise. NOT gate inverts any input that you have. So if you have a 0, your output is a 1. If your input is a 1, your output is a 0. In most of the questions that you will have, you will usually be allowed to use inversion bubbles to represent a NOT gate for your gate inputs, but not on your gate outputs. So this is what it would look like if you had an AND gate and you were allowed inversion bubbles. This is the same thing as writing your gates like this. It's just a tool to save space. Okay, so I'm scrolling forward. We'll work through an example with all these gates. This is just our third topic that we're going to introduce is sum of products and product of sum equations. When you have a sum of products, your SOP, your equation is used to describe wherever a function is 1. So your literals in a sum of products equation where you have A, B, and C will have a value of 1. The complements of those, A naught, B naught, and C naught, will have a value of 0. So in this example where you have a sum of products equation, each of these terms will have like a value of 1. Each term shows you exactly which set of literals will produce an output of 1. SOP circuits are typically just 2 levels. You've got multiple AND gates and a single OR gate to tile those outputs from the AND gates together to produce one single output. And then in a product of sum equation, it's kind of the opposite. You have an equation that describes everywhere a function is 0. So literals in a product of sum equation have the opposite value of what they do in a sum of products. So literals A, B, and C will have a value of 0. A naught, B naught, and C naught will have a value of 1. This is an example of a product of sum equation. You can see that each of these is a sum and they are tied together with a product. Similar to sum of products circuits, product of sum circuits are 2 levels. The first level will just have multiple OR gates or with as many inputs as you need. And then your second level will just be a single AND gate tying all those together. Okay, let's work through some examples. In this first one, you'll typically be given an equation and asked to draw a circuit. So the trick is to kind of work from inside parentheses and work your way from left to right. So I'm going to write this equation here. F is equal to A or B naught and B, or C naught. As a refresher, the plus sign means you have an OR gate. If you have like a multiplication symbol, that usually means it's an AND gate. And then the prime operator, or sometimes you'll see circuits like C bar or C prime, that's when you have a NOT. So for this equation, I have two OR gates. The first one, is going to tie inputs A, and then I'm going to use a NOT gate here, and A or B NOT. My second OR gate over here is going to be for the second term. I have B or C naught. And I'm going to use an AND gate to tie the outputs of both of these OR gates together to obtain F. And if you recognize the form here, this is in a product of sum form. So you've got multiple OR gates and one AND gate in like a two-level circuit. This example over here on the bottom, example E, is one of those where you're given clear instructions that you may use inversion bubbles as instead of NOT gates on gate inputs, but not outputs. So read your questions carefully. Make sure that you're not using the wrong kinds of inputs. So over here, you've got F is equal to A or B naught. The whole thing is a naught. And B and C naught. The whole thing is inverted. Right, so working from left to right, you've got an OR gate tying A and B. I'm going to draw my second one over here. I have B and C naught. Right, now I'm going to tackle these NOT gates here on the outputs. I'm going to draw a NOT over here on the gate output of each one. And the last step in drawing the circuit is putting this AND gate. So I'm going to draw one here. And then that is your circuit. Yes.
When it says you use inversion bubble inputs the OR and the AND, but not their outputs, it's still okay to put those.
So these are your inversion bubbles. Those are only okay on the gate inputs. If you have, if you need to use a NOT on a gate output, you're going to use a full NOT gate.
Okay.
Yeah.
You cannot put a circle like on the right side.
Yeah. So yeah, this is not what you want to do here. This is an entirely different type of gate. So yeah, but this is okay over here. I'm just putting a NOT gate like this. Yeah.
Curiosity, is it possible for you to simplify like further? For example, put the knot outside of the parentheses, inside the parentheses, so that it becomes A naught plus B times B naught times C.
Yeah, you could be able to like apply De Morgan's law, but as the question says, do not simplify the equation. The circuit that you have over here has to match the exact, like the original equation that you've been given.
They make it that way just so like they understand how the gates work. So it is more complicated, but it's just so they know that you know what you're doing.
Okay, makes sense.
But in a real world, yes, you would simplify it.
Yes, yeah. All right, so moving on to our last example on here. When you're given a circuit and asked to write an equation, work from left to right to write out each, like transform each input. So starting from your input x here, when x goes through a NOT gate, it becomes x naught. I'm just going to write y over here so I can see what it looks like at the AND gate. You've got x here, and then you've got z naught. So at the output of this AND gate, you've got x naught and y. At the output of this AND gate, you've got x and z naught. This here is an OR gate, so going to OR the inputs together, OR x and z naught. So your final answer would be G is equal to x naught y, or x and z naught. Yeah? Any questions before we move on? Okay.
I would also like to say for drawing the circuit, you'll notice that Varsha started off with drawing what's inside the parentheses first. You kind of want to, like, whenever you draw it, something out that way. Start inside the parentheses and then all the parentheses, like the combination between them. At the very end.
Okay. Moving to our third topic, timing diagrams. This here is an example of what timing, well, this is what timing diagrams look like for when you're given an input and you're showing how the output changes over a certain number of units. So in the case of this diagram, I wonder if you can see the blocks, but each block is just like 1 unit of time. So in this first timing diagram here, you have an AND gate. So for inputs A and B, this is what the output would look like here. It's important to note that the outputs on a timing diagram match up exactly with what the values in your truth table are. Right, so you've got A is 0, A is 0, 0, and then 1, 1. B is 0, 1, 0, 1, which gives you 1 here for A and B only when inputs A and B are high. All right, so this is how you would interpret a timing diagram. You've got the diagrams for both the OR gates and NOT gates for A NOT and B NOT at the bottom. We'll work through an example just so you can see how it's relevant. But when you're given an equation or a circuit and you're asked to generate the timing diagram for it, the first thing you're going to want to do is write a truth table. It's the best way to make sure that you haven't missed any of your inputs. Oh, there's just like giant gaps there. Okay, so in your equation here, you've got 3 inputs. So that means you've got 2 to the 3, 8 outputs. So in my truth table, I'm going to have A, B, C, and F have 0, 1, 2, 3, 4, 5, gotta squeeze this in, 6, and 7. Okay, I'm actually going to split up this F here to have A or B not. And then this is just to make sure that we don't make any mistakes while we're calculating the output F. Yes. Oh, I see. Yeah. Thank you. Let me zoom in there. Okay. So where you have A or B naught, you've got 0 or 1, which results in 1. 0 or 1 to 1, 0 or 0. It's going to be a 0. 0 or 0 is here. You've got 1 or 1, and then 1 or 1, 1 or 0, 1 or 0. That should be the values for A or B naught. Here where you have B and C, you've got 0 and 1. Wherever you have a 0, it's going to be 0, and then the whole thing is knotted, so this is a 1. Actually, I'm going to write it a little bit to the side. So I have 0 and 0 not, which is going to give me a 1. I have a 1 and 1 not. That's going to give me a 0. Got a 1 and 0 not, which is going to give me a 1. Timing diagrams take a while, y'all. Okay, then you've got 0 and 1, the whole not, so that's going to be 0. You've got 0 and 0, the whole not, so that's a 1. You've got 1 and 1 not, so the output's a 0. You've got a 1 and a 0 not, and that output's going to be a 1. So F is these the values in this column and the values in this column. So 1 and 1 is 1, 1 and 1 is 1, 0 and 0 is 0, 0 and 1 is 0, this is 0, 1, 0, and 1. So these are the values for F for A, B, and C. Okay. So I'm going to start building my timing diagram here, A, B, C, and F. Right? Okay. I'm going to write 0, 1, 0, 1, 0, 1, and 0, 1, just to indicate what the 0 position and 1 are. Okay, so for 0, A is 0 for 4 units of time, then it is 1 for another 4 units of time. B is 0 for 2 units, 1 for 2 units, 0 for 2, and 1 for 2. Oh no. This is what happens when you let the shape tool take over. Okay, great. and then C is 0, 1, and 0. Oh no. Okay. Okay, C is just going to look a little ugly, but it has all the values. There we go. Okay. And then F, you're just going to go like from time 0, F is 1. At time 1, at time 1, F is 1. At time 2, it's 0, 0, 0. Then F jumps up to 1. F jumps back down to 0, and then becomes 1. So that is what F would look like for inputs A, B, and C on a timing diagram. Okay. So for this next equation, I'd like to use a little bit of trick by first recognizing that this is a sum of products. It's in a sum of products form, right? And if you remember before, we've said for sum of products equations, you've got, we'll just use x, y, and z have a value of 1. X naught, y naught, and z naught have a value of 0. So in lieu of going to a truth table, you can figure out exactly which inputs are 1 and exactly which inputs are 0. So where did it go? So I'm just going to write out the truth table anyway, just so we can see what that would look like. And then G, 0, 0, 0, 1, 2, 3, 4, 5, 6, and 7. Okay, so based on these values here, this is saying, this first term here is saying that you will have a 1 wherever x is 0 and y is 1. So if we go to our table here, x is 0 at these points, y is 1 at these points, right? So I'm going to put a 1 at both of these. I can ignore all the other values because over here, x is 1. That doesn't match that first term. X is 0 here, but y is also 0 here. So these are the only 2 points where that first term is going to be 1. For the second one here, x and z naught, g is going to be 1, where x is 1 and z is 0. So when I look over here, x is 1 here and z is 1 here. Sorry, x is 1, z is 0, x is 1, z is 0. So these are other 2 points where I'm going to have a 1. Everywhere else, it's just going to be a 0. And y'all, if this is confusing, just go step by step like we did for the first problem to figure out what the values in your truth table are. But this is what your function, the output at G is going to be. So when we're drawing out our timing diagram, not A, we've got X, Y, and Z, and G over here. All right. So X is 0 for 1, 2, 3, 4, 1, 2, 3, 4 inputs. Y is 0, 0, 1, 1, 0, 0, 1, 1. Z is 0, 1. That's what Z would look like. And then G is 0 for the first 2, 3, 1 for the next 3 time, and then 0 up to 1, and then back to 0. So that's what the timing diagram for G would look like. Oh, you see, okay. Okay. I understand that y'all can't see the time 0. I'm going to draw these in gray just so you have the grid. 0, 1. Yes.
At least regarding the and statements, I just want to make sure like this is 100% in my head. If let's say values A and B, they're an and statement, both were 0, that would equate to 1, like
That would equate to 0. So for AND gate, both the inputs have to be A1. So if any input to an AND gate is a 0, then the output is automatically 0 because if one input is 0, then both cannot be a 1. So AND gates, the inputs do have to be the same, but they both have to be A1 as well. They have to be on in order for on to be on.
and if they were inverse, then that become 1, right?
If there was an inverted gate after, then the 0 would become a 1.
Becomes 0. I'm wondering on 3.
Oh, I think these are a little off. That's my bad.
With where C is equal to 0 and A plus B
Yeah, that's
is 1, and then it has 0 times 1, not 0. I'm just wondering on that part, presumably it would become 1, right? And then it reverses to 0?
You're talking about this one?
Yes,
Oh, did I mess up on one of them?
So let's see,
without an error.
what is your B input for,
Oh, let me scroll over.
okay, so for this one, B input is 0, so 0. C, is 0, but it's non-use, it turns to a 1. And then all of this would be equal to 0. Yeah, so this should be a 1.
Oh, that's my bad.
Okay, I thought I was going crazy.
Okay.
I was like,
Yeah, thank you. Okay, so that should be a 1, which means this is a 1.
Please do say something, and if you're wrong, then just be alert.
Okay, so it's for this one, right? 1, 0, 0. Okay, so it's 1, 0, 0. So this one here should be a 1. Okay. Yes, I believe that should be right now. Okay. Okay, so moving on to our third example. I'm going to apply that same little shortcut logic where I recognize that this is a product of sum equation, which means my inputs A, B, and C are going to be have a value of 0, A naught, B naught, C naught are going to have a value of 1. Again, break this down into a truth table if this like little skips in logic are going to be a little tough to figure out. A, B, C, F. Okay, and we're going to cram the numbers at the bottom. 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, and 7. Okay, so looking at my first term, F is going to be 0, where A is equal to 1, where A is equal to 0 and B is equal to 1. So I'm going to look at A is 0, B is 1, right here. So this is going to give me F is equal to 0. It's a product of the sum equation, so your F is, this equation tells you where F is 0. That's what we're going to put in. We're going to put in the ones later to put in our timing diagram.
If you're confused about like how to convert that to a truth table, the whole POS, you can also just input the
Yes, input each values of A, B, and C and work out the truth table like we did in this first example. Just in the interest of time and so that you guys have like an extra way to convert, just showing you this one. And then here, B is going to be 0, C, so you're looking for values wherever B is 0 and C is 1. So that's going to be here, B is 0, C is 1, and over here, B is 0, C is 1. So I'm going to put a 0 over there, put a 0 over here. And then everywhere else is just going to be 1. All right, is everyone with me? Okay, and I'm going to just copy these lines over. Copy. So y'all can see the same grid that I'm seeing. Okay, I think that's a little bit off. Okay, sorry y'all. I think we're just missing a couple lines. Okay, just bear with me. I'm seeing a full grid on my page and I understand y'all are not seeing that on yours. Okay, I think that should be 8. Okay, so for A starting from time 0, 1, 2, 3, 4, 1, 2, 3, and 4. B is 1, 2, up for 2, down for 2, up for 2. C is up and down. And then F starts off at high, high, down for 3 inputs, up for 1, down for another 1, and then up for 2. Okay. Any questions? Can y'all see all the numbers and everything up there?
I kind of just want to ask really quickly about the POS form that is requested.
Yes.
presumably it can also be applied to the SOP form, like whatever you have done right there. It's just that I'm having a bit of a gap in knowledge or understanding like what's going on with the POS form.
Mhm.
Why A, B, and C equals 0, and A not B not C not
Sure.
equals 1.
I can go up to the table that we had. It's one of those things where because a POS form has to describe everywhere the function is 0. So for example, this equation here, can you all see this here? Okay, if we were to assign 0, so if we were to say 0 or 0 or 0, remember for an OR gate, your input is 0 wherever all inputs are 0, right? And then we're going to say, oops, this is just like a random equation. It doesn't really have any bearing to some of the other examples that we've seen. 0 or 1 or 1 here. And then I'm just assigning the values to each literal based on the table above. 1, 1 or 0. Okay, so if you were to take each of these values and just do the ands and ors, the resulting value for f would have to be 0, right? And each of these literals are just telling you exactly where in the truth table your values are 0 for f. I could always draw for that particular equation that we were talking about, just draw out the truth table so you can see that it corresponds. Would y'all like to see that?
For me
Okay.
personally, it's fine. I just didn't know, like, understand that part since
Yeah.
I'm a little bit late as
No
well.
worries. Okay, let's just add a blank over here. So we've got, how are we doing on time? We're good, right? A or B naught, and then B or C naught. Okay, so we got A, B, C, B naught, B or C naught, and then F over here. Okay, 0, 0, 0. 4, this is 5, 6, and 7. Okay, so for this first term, you have A or B naught. Let's writing in blue. You got 0 or 1, which gives you 1, 0 or 1, 0 or 0, 0 or 0, oops, 1 or 1, and then 1 or 0 is going to be 1, 1 or 0 is also going to be 1. So those are all the output values for that first term. For the second one here, you've got 0 or 1, it's going to be 1, 0 or 0, 0, 1 or 1, 0 or 1, this is 1 or 1, and then you've got 1 or 0. Okay, and then F is each of these values in blue combined with an AND gate. So 1 and 1. This is going to be 0 because it's 1 and 0. 0, 0, 1 and 1, 0, 1, 1. Yeah? So this is your truth table. So when in doubt, go with the full truth table. You will not go wrong unless you mess up on that too, but that shouldn't happen. And then you go the same way. So you can go from equation to truth table to timing diagram. I'm just going to abbreviate that CD. Okay. Any more questions on the timing diagram example? Okay. Okay, this is I think our fifth topic for today, K-maps. K-maps typically come in 4 variable, 3 variable, or 2 variable. They are just a tool for you to visually minimize a circuit. So y'all have done those Boolean equations with applying all the properties to minimize. K-maps help you simplify that a little quicker because you can see which terms can be grouped together to be simplified. These are some of the steps to simplify a K-map. As I understand it, y'all only have to populate a K-map from an equation or a truth table for the exam, but check with Dr. Kogan if that's not the case, like if you have to simplify it, etc. So the following examples here are just going to show you how to fill in a truth table. Sorry, fill in a K-map from a truth table or an equation. Some of the key ones I'm going to show on this for variable K-map is your inputs over here have to go from 0, 1, 3, and 2. And the same on this side over here. This is just so that when you look at the variables here, let me write these out. Because you're looking for variables that, don't change is what I believe that we call it, C and D naught. If you look at these two variables here, the ones that are common here is the variable D. If you look at these ones on this side, the ones that's common is C naught. Ooh, I think I messed up there. But yeah, so this is how your K-map should be organized. Is something that you have to memorize in order for you to do your K-maps correctly. I'm just going to erase those texts in red. It is always helpful to write out what the value of each cell is in the K-map, because these correspond to the row of your truth table. So in a 4-variable K-map, you have 16 outputs. It goes 0, 1, 3, 2, all the way to 12, 13, 15, and 14.
If you forget the order, you can just look at, for example, take this one. Just look A, B is 1, 0, and then C, D is 0, 0. So 1, 0, 0, 0, that's 8 for the decimal. If you ever forget, it's just a decimal equivalent of the binary.
Yes, yeah, those are what the little values in the cells are. Okay, well, let's just work through an example. It should start making a little bit more sense. So for this first one, you're given a truth table and asked to write a K-map. If you look at it over here, this is a 3-input truth table, so 2 to the 3, which means you'll have 8 outputs, right, which you can see 8 rows on your truth table here. I'm going to draw this giant grid. And then 2, 3, 4. Okay, so 0, 1, 0, 1. Okay, and then I'm going to write my variable A on this side, B and C on the side of the diagonal. I'm going to number each of these blocks. So this is going to be 0, 1, 3, 2. Those numbers, again, correspond to the decimal value of the binary that's associated with each one. So 4, 5, 7, and 6. So then I'm also going to number my rows of the truth table here, just so when I'm 5, 6, 7, when I'm transposing each one, I'm not messing up. So starting from the top, 0 is 1, 1, 2, 3, and then I've got 4, 5, 6, 7. And that's how you fill in your K-map. Right? Okay. I'm going to go on to the larger one. This is your 4-variable K-map. Stop me if you have any questions or if you see something wrong. It's going to be a really ugly square, but it'll look nice. Okay. Okay. And then on the left side of the diagonal, I have WX. On this side, I have Y and Z. I'm going to 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. So 0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 15, 14. Okay, and then I'm just going to go one by one on each of these rows. So I'm going to number these as well. 0, 1, 2, 3, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15. So 15 rows. And then I'm just going to start filling these in. So 1, 1, 1, 0, 1, 1, 6, 7, got 8, 9, 10, 11, 12, 13, 14, 15. And that is a completed K-map for that second example. Any questions? All right, we've got one more example to work through. Well, it's just 3. So this one asks you to create a truth table for the function h that's represented by this K-map. Same as the one example that we've done before. I'm going to have w, x, y, z. And then, let's function h. Yes. is
Usually they stick between decimal and
Okay.
binary from what I've seen, but you should know how to at least do hexadecimal from binary. Octal, which is something that's touched in like your game stuff, you have very less chance of seeing that. But so if you had to focus, I would say binary decimal.
6,
Just those three.
I'm mostly just
7,
concerned about the fact of negative,
Eight,
negative binary.
That'll
10,
be, don't worry. We have
11, 12, 13,
this is all recorded and will be
14,
posted on the
15.
YouTube.
Okay.
I'll send in a link to your teacher as well, so
Perfect, thank you so
you'll
much.
be able to watch it.
Okay, so I've just written out my 16 rows of for my truth table, and then I'm just gonna go start from just start going like row by row. So this is 0, 1. Remember that it is organized as 0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 15, 14. So I've got 0, 1, 1, 3, 2, 4, 5, 7, 6, and then I've got 8, 9, 10, 11, 12, 13, 15 is 0, 14 is 0. And that is a truth table for that associated K-map. The question also further asks for you to put the min terms and max terms in canonical form. Megan's going to go over that in just like 1 or 2 slides, so y'all can come back to this example later to work on it. Okay, so for this equation up here, f is equal to a naught and d, or a and d naught. The first and best option is to go from equation to truth table to K-map. As I've done before, you recognize that this is an SOP form equation, right? So hang on, I'm going to draw my K-map out so I can show you guys. 1, 2. Remember that SOP equations tell you wherever a function is 1. So that's 16 cells. And then that's A, B on this side, C, D on this side. 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. Okay, so in an SOP form, A and B have like a value of 1. A naught and B naught have a value of 0, right? So following through that, in this equation, you're looking, you have a 1 where A has a value of 0 and D is 1. All right, so I'm going to highlight here. Wherever A is 0, so that means these 2 rows, and wherever D is 1, that's here and here, I'm going to list 1s. So A is 0, D is 1, A is 0, D is 1, A is 0, D is 1, and A is 0, D is 1. So I've got 4 1s in my K-map that correspond to this first term here. And then I'm going to repeat the same thing with my second term. I have 1s wherever A is 1 and D is 0. Right? I'm going to put that just highlighted here. These 2 rows are where A is 1. And then these 2 columns are where D is 0. So if I'm putting in my 1s, A is 1, D is 0 in all of these spots. Right? And then wherever there's not a 1, there will be a 0. So I'm just going to fill in the rest of my K-map with zeros. Again, the best option is always to go equation to truth table to K-map. You will not go wrong that way. This is just like one of the other ways that you can do it. Okay, any questions? Okay. So for this third equation here, I'm going to rewrite it down here. T is equal to X or Z and W naught or Y naught, Z, W, Z naught. Okay. And I'm going to draw my little K-map on the side. It's going to be a smaller K-map. Oops. Okay, 0, 0, 0, 1, 1, 1, 1, 0.
And while Mark is drawing the K-map, I also want to say, if you guys are on the iTunes Discord, then you can always send a message in the hashtag student channel. Like if you ever have a question, you watch your video and basically any tutor will be able to help you because it's an intro course, and there's many tutors that will help you either on call or even late at night. I've seen people answer at 2 a.m. So just send a message or come to an office or come to a tutoring hour for somebody, and then get that question sorted out before the exam.
Okay, so yeah, this equation is in a POS form. If you are not sure, go to the truth table, but in this case, it's a POS form. So your literals W, X, Y, and Z have a value of 0. Literals W naught, X naught, Y naught, and Z naught will have a value of 1. In your K-map, you're going to be filling in zeros first because you've been given a POS equation. All right, so I'm just going to go term by term. In this case, X has a value of 0. Z has a value of 0. So in my K-map, I am going to put a 0 wherever X is 0. So that's in these 2 rows. And where Z is 0, that's these 2 columns. All right, so I'm going to put it in here. 0, 0, 0, and 0. Yeah. And then for my second term here, W naught has a value of 1. Y naught has a value of 1. Z has a value of 0. So it's nice when you have 2 variables here that are on the same side. So I'm going to find wherever W is 1, which is over here in these 2 rows. And then I have Y naught or Z. So you're looking for the column that is 1, 0 here. All right, so I'm going to put in a 0 here. There already one, I'm just going to circle over it, and then there's one over here. And then there is one here. Because it's where W is 1 and Y or Z is 0. So I'm going to circle that. Yeah. Okay, and then for this last term, you've got where W has a value of 0, X naught has a value of 1, Z naught has a value of 1. So on my third color here. On this row, you're looking for a 0, 1. So that's this entire row. And then Z naught, wherever Z has 1. So I'm just going to add zeros into these 2 spots. I'm just looking at like the intersection of where those 2 rows are. So I was to look at like this. That's where I would put my zeros. Okay. And then again, with the K-map, you have wherever there is not a 0, you have a 1. I'm just going to fill those in. And that is the fast way of going from equation to K-map. Okay, any questions, y'all? Our next topic is Boolean algebra. This is just a table of all the Boolean properties that you will have learned in class. I organized it just so that, because complement and idempotent properties, it just made sense for me to look at them this way. It is a very useful table to memorize. If you do not have it memorized, don't panic. You're always welcome to write out little truth tables at the beginning of your exam, just so you remember exactly what properties are and what the outputs would be for any given 2 inputs. The 2 other key properties here are distributive and over or and or over and. We're going to see how we're going to use that to convert between product of sum and sum of product forms in your examples coming up. Okay. For any of these questions, since y'all have learned K-maps, it's very useful to draw a K-map out for each equation so you can see which terms can combine or to be simplified. It's also a great way to check your answer if you've got a really long, complicated problem.
So I know on a lab that you guys, like, I think Justin kind of helped somebody on it today. There was a tricky question on it where you had to duplicate a term to use it in 2 different pairings. That's a trick that you can't really find unless you have a K-map. And by that, can you draw like a small example?
Yes.
K-map.
Let's do it over here.
Just to show you what example is, I'm pretty sure you've seen it in the lab because it was a question. But
Okay, let's do this.
I'm just gonna draw like a little quick example real quick. Chances are you might not have this on your exam just because it's kind of a tricky question, but if it's on your homework or lab, there's always a chance for it to be on the exam, so we just want to kind of introduce it.
Okay.
Just do like a pair up.
Oh, okay. So if you got like ones over here,
So
and then I've got 1.
Up, down pairing, and then left, right. In that case, this term that's being used twice, if you were to just list these 3 terms and then do Boolean algebra without a
So if
K-map,
I
you would
had
actually get the wrong answer. It would not simplify down fully. And if we have time at the end, we can do an example of that.
Yeah.
But in this type of question, you have to duplicate this term that's being used twice. You have to write it twice. That way you compare the top one with it and the one to the right with it. Otherwise, it will not simplify down.
Yeah.
Exactly.
So this is your duplicated term here. I'm just writing it all out just so you can see that this is, after this, you're going to go ahead and factor them to figure out what the simplification is.
Really quick question, I just want to make sure. So whenever we have, let's say, those trick questions, would it be best to create it first the K-map and then work backwards?
I always say draw the K-map first.
Mhm.
K-map first and then work backwards. Okay, easy enough.
Because also sometimes they might put your terms out of order a bit. So like your first term might combine with your third, and your second term might combine with your fourth. And in that case, you would try first to combine the first and second term, and then you do like first and third, first and fourth. It's a lot more work. So what the K-map can do is it can show you which terms actually go together. So you don't have to spend all that time trying to find which one's paired.
Mhm.
This one will tell you which one's paired, and then you don't have to spend time searching. It's also a go-to checker.
Mhm.
Check your work.
Okay, I'm just going to minimize this and move this to the side in case anyone has any questions about this one later. Put it over here. Okay, so when you're given an equation and asked to convert to an SOP form, this is a really great spot where this table is handy. I'm going to screenshot it and move it to the one that we're working on. And copy. Because I always find it difficult to remember exactly what which property. Oh no, sorry. And then I'm just going to have this here. For y'all who can't screenshot on an exam, just write out your little table and like a scratch piece of paper so you can compare and look at it. So the first thing you're going to do here is apply your distributive property and over or. So I'm going to abbreviate it for dist and or. And you're just going to distribute it out. So here, I like to put all my literals in alphabetical order just so I can see them. And then it's A, C, D naught. You have B and C naught and D naught, or A and D naught. Oh, nope, sorry. I did this yesterday too. C naught, D naught. I put in an extra A over there. Okay. And then I'm going to use your commutative, which is kind of like your basic math property, just shift the terms around, just so I have all the terms that have common things together.
On your exam, you will not have to know names, by the way. Names is just for homework and all that. They just kind of want you to look back and see that like
Mhm.
you used the correct property. But on an exam, you are not expected to memorize names.
Mhm.
You just got to do the property.
Yes. Yeah, don't worry about the names. Just know that, so these two terms have a commonality. I'm just going to group them together here. These two other terms, we can come back to it. But here, I'm going to factor out a C naught and a D naught, which leaves you with a 1 or a B. If you look at your properties here, it is an example of the null property. This whole thing will turn into a 1. Just going to write null, and then I'm also going to apply the identity property, which means anything and 1 is basically what anything is. So this is just going to leave the C naught and the D naught term behind. So I've got A naught, B C naught, A D naught, C naught, and D naught. There's nothing that can be done with these two terms to simplify them, so we're just going to leave them as is. And then this is your final equation. Y is equal to this. Okay. I'm going to move my table over here. Go ahead and assign properties if you'd like to just recognize which one is which for each equation. Okay, and then here you're given an equation in an SOP form, Q R naught S naught, Q naught RS, and asked to convert it to POS form. This is where your distributive or over and property comes in really handy. So I'm just going to go term by term to break it down. You've got Q or Q naught. Find that distributive or over and property. And Q or R and Q or S. All right, everyone see where it's coming from, right? And then I'm going to keep going. You've got R and then Q naught, and R naught or R. And then you've got R naught or S. For the last one, you've got S naught or Q, and S naught or R, S naught or S. Okay. these ones, this is my favorite part, where you look to see and you can apply the complement property. So where you have Q or Q naught, that is a 1. R or R naught is a 1. This one is also a 1. So I'm going to bring down my equations here. I have Q or R and Q or S. And then I've got R naught or Q naught. Do S, Q, and S naught or R. Okay. Then I believe that these two terms here, you can also apply the complement property for. So that I'm just going to put them as 1s because you've multiplied those two together. And then I don't see that you could apply that for anything else. So your resulting equation would be Q or S and R naught or S naught or Q, S naught or R. So that, yes.
So, that first pair of 9 that you have up top, the way that you did it, you did a Q times like the first literal and like the first portion, you multiplied that, or sorry, or that.
Yes.
With each literal in the second.
In the second term, yes.
Okay.
Yeah.
Are all those 9 multiplied together? So
yes. Yeah, because you have the and operator. I guess I could write this a little bit like this. Come on, cooperate with me. Oh, I see. Okay. Okay.
I think how she would do it, she would like group up like the first couple and then like, I don't know.
Okay.
That way is kind of confusing, but this makes more sense.
Okay. Yeah, this is the way that I'm most familiar with. It's like when you see here your or over and property. I guess sorry, this is an and over or also. You got A and B or A and C. You're applying the same logic here, but you're kind of going like backwards from your SOP form to there. Yeah. Oh, I see. Okay. Yeah, that would just give you like more lines to have to break down. This is the way I've learned it. Yes.
So if there was another,
No, keep going, keep going.
if there was another portion or to that, would it be like the same thing?
Yes. I would recommend then you kind of go like 2 terms at a time. It's easier when you can like find a complement property and get rid of some of those terms. And then you just keep going, like go 2 at a time, just so you don't have like a mess of like 100 terms to deal with. Yeah.
On the test, you will most likely not be given like 4 different terms because those get very long. I'm sure you had on your homework. But yeah, test will not have to. It'll be more like this, kind of shorter.
Mm-hmm. So these 2 terms, right? Applied for these 2 terms. Yes, I believe so, and I think you'll learn this a little bit later. But this format is kind of like for a different kind of logic gate. I think we can draw the truth table later if we have time, just to prove why this one you can't apply to the complement property just to get rid of them. Yes, it should be the same. Yeah, and one should just be like the literal form. One should be the complement form. When in doubt, put a little truth table. Those will never lie to you, as the name suggests. Okay, I'm just going to copy my properties here. If I was writing out all the properties, I would use that table, but in the interest of time, I'm not going to. So you're given this equation H in product of sum form, and you're asked to convert it to sum of products form. You are going to apply the distributive property, and here I want to go like 2 terms at a time, just so I can simplify things that can be done. So I've got this first set, A not B, or wait, yes, A not, C not. Sorry, I just suddenly blanked. I think I'm going the right way. Yeah, okay. And then in my second set of terms, I'm going to say A B not, A C, B not C, C C. Okay, so in this first one, I recognize 2 properties that I can use here. This first one here is your complement property, which means this is just going to be 1. The second one over here is your idempotent property, which just gives you one single term C. Right, okay, and I'm going to keep distributing here. So I've got A naught, A, B, and B naught. Again, I like to put things alphabetically so I can see how the properties apply a little easier, but I'm just going like first term to the first term and then rearranging those literals. So I've got A naught, A, B, C, A naught, B, B naught, C, and then A naught, B, C. Oh, I'm so sorry, I made a little mistake here. C and C naught is 0 according to the complement property of and over here. That'll come in handy later. Okay, and going on to the second term, I've got A naught A, B naught C naught. I've got A naught A, C, C naught, A naught B naught C, C naught, and A naught C naught C. Okay, and then for my third term, I've got A, B naught, B, C, A, B, C, C. I've got B, B naught, C, C, and then I've got B, C, and C. So for this last term, because I've identified that it was 0, 0 times anything is going to be 0, so I'm not going to bother to write out that last set of terms. And then I can go ahead and start simplifying over here. So we can apply complement property to a lot of these. A and A naught is 0. 0 times the whole term is just going to be 0. Okay, I see that property can be applied here. Here it's going to be for B and B naught. Nothing can apply here, so I'm going to leave that alone. You've got A and A naught, A and A naught. You also have C and C naught. Here you have C and C naught, so that term is 0. C and C naught, that term is 0. B and B naught, that term is 0. Here you can apply the idempotent property, so this is just going to be C. B and B naught is 0, and then again C and C is just C. So I'm going to write out the terms that are not 0 here, A naught BC, or ABC, or BC. Because it's asked for sum of products form, this is going to be your final answer. I know you think we can like keep simplifying, but I don't believe there is any point. Oh, sorry. Yes, BC, A naught, A, or 1, just because I'm pulling something common out of there. A or A naught is 1. Here, 1 or 1 is just 1. And then you're going to apply that B, C, and 1 is going to be equal to BC. Sorry about that.
For these
Yeah.
columns, these SOP and POS, you do not have to simplify at the end unless it tells you to. All they want you to do is just
Yeah. So this could be considered this could be your final answer.
The most simplification you should just use in like the terms itself that you got, but you don't have to like redistribute or like anything like that.
Mhm.
Pull out any like equal significance.
Yeah. So that you can just stop there. If you like to keep going, you can, but I guess if it doesn't tell you to, just don't do it. Yeah. Okay. Any questions here?
Also, the checker, your POS, and your SOP should give you the same values for your output. So if you draw a truth table for both, they should give you the exact same. They're just different ways of writing the same exact function. So if they're giving you opposite values, you did it to Morgan somewhere or something like that.
Okay. I think you can take over from here.
Okay. So let's continue, unless anybody has questions real quick. Yeah. Oh, this whole thing's going to be recorded, and it's going to be posted on UTD IEEE YouTube. There's a channel, actually. You'll actually find past reviews on there, too, if you ever want some more practice. There are past reviews already there. There's one that's called 2310 Test 1, I think, from last semester. So, yeah, this will be posted. We'll send a link to your teacher, too, so she can tell you guys, but do not worry. Okay, so we're going to move on to midterms and max terms. So midterms is where the function is equal to 1 at the end, and it's actually in the form of SOP, so the one you guys are probably most familiar with. We'll get to the compact notation of those later. For max terms, it's where it's equal to 0. This is the product of sums form. So this notation thing here is if it says to put it in compact notation example, what these numbers basically mean is just, so on a truth table, when you have like values of A, B, 0, 0, 0, 1, 1, 0, 1, 1. These numbers are basically just the decimal value equivalent. So the number for this row would be 0, this one would be 1, this one would be 2, and 3. And you'll notice it just counts up. And this will be more, you'll learn more about this in the example that comes. So just wanted to do that. The symbol for compact for midterms is a sigma sign. And then this symbol for max terms is a pi sign. Okay. How I like to remember it is midterms is sum of products form. So you would use the summation symbol for that. And then the other one is pi. Okay. So use the following truth table to answer. Write the function as a literal sum of midterms first is what it's asking. So like I said earlier, sum of midterms, you're going to look for where the output is equal to 1. So we have right here, here, and here. Those are all our ones. Whenever we talk about midterms and max terms, we have to use all literals. You cannot just be like, oh, this simplifies down. No, this is not simplification. You use every single letter in each term. Okay, so for this first one, we're going to do A naught. I'll zoom in a bit. A naught, B naught, C naught. The second one is A naught, B naught, C. This next one is A, B naught, C naught. And this last one is A, B, and C. So we're going to put this all in sum of products form. Write the, oops, how'd that change? Write the function as a literal sum of midterms. So we're not going to simplify, put it all in. We have A naught, B naught, C naught, ORed with A naught, B naught, C, ORed with A, B naught, C naught, ORed with A, B, C. No simplification needed, okay? It wouldn't be a midterm otherwise. We'll get to compact sum of midterms after. Let's just do the literal products of max terms next. So now we're going to be looking for where it's equal to 0, because now we're representing the function as where it's equal to 0. The very opposite. They're like opposites of each other. And this is where you get into that weird products form that Varsha was talking about earlier, where it's kind of like the opposite. So here, A is 0, so we're actually going to do the opposite, and we're just going to put A. We're not going to put A naught. ORed with B is 1, so we're actually going to put B naught. ORed with C is 0, so we're going to put C. It's like the opposite of what you think it should be. Okay. Next one, we're going to go a bit faster. It's going to be A or B naught or C naught. Next one is A naught or B or C naught. And then this one is A naught or B naught or C. Okay, so we're right now, because there's a lot on here right now, these are the ones we're looking at. Okay, we're going to write it as a function of literal product of max terms. This is in POS form. So we have the first one was A or B naught or C. Second one is A or B naught or C naught. Next one is A naught or B or C naught. And last one is A naught or B naught or C. Okay? So now the compact version is a lot easier. Okay? Basically, you know how I said that the numbers represent what the binary is in decimal? So on the left, we're just going to write that down. This first one is 0, 1, basically counting up, 2, 3, 4, 5, 6, 7. Make sure you start at 0 because you have 0, 0, 0, right? And basically, we're just going to look. Okay, so we're doing compact sum of midterms, which I said is the summation, because we're in sum of products. Summation. And we're going to look at which decimal numbers is our output equal to 1. So we have at 0, our function is 1, so we're going to put a 0. We have at 1. We have at 4 and 7. So I basically put the numbers that correspond to the blue color. Okay. For compact product of max terms, it's the exact opposite. So we have the pi symbol, and now we're looking at the red circles where it's equal to 0. So we have 2, 3, 5, and 6. So you have to make sure these two should not be sharing any numbers, because an output cannot be both a minterm and a max term. It can only be one. So you should be including every single number, but they should be split up. None of them should be repeating. Okay. Any questions on minterms and max terms so far? No? Okay, let's move on. So now we have another one in which it wants you to write F1 as a sum of minterms and F2 as a product of max terms. Numerical form. So it's saying numerical, this is the same thing as compact. This is where we use the numbers. Okay? So you don't got to do all the literal work, just the number. So on the left, I'm going to write the numbers 0, 1, 2, 3, 4, 5, 6, 7. And we are going to look now for F1 is equal to minterms. Minterms, remember, is where it's equal to 1, so these. And we're going to say, okay, so we have the summation, and we're going to say, okay, F1 is a 1 where it's 4, 5, and 7. Okay? F2, so these are minterms. F2, it's saying product of max terms. So for F2, we're going to be looking at every single 0. And we're going to say, okay, well, at 0, 1, and 7, we have a 0 as an output. Notice we have a 7 being used in both, and that's just because we're talking about two different output functions. Okay. De Morgan's. So you're familiar with the notation on the left with the apostrophe. I'm going to introduce another notation to you, just because personally, I think it's a lot easier to visualize and keep track of. And the same with the people I've taught. You're allowed to use this in Kogan's class. Just make sure that at the very end you change it back to apostrophe notation, which shouldn't be an issue because you'll be putting this into a computer anyways, so you can't really put the bar notation anyways. You have to put the apostrophe. But I'm going to do them both side to side so you can see and see which one you like better. So basically, whenever you De Morgan's, you put an inverter at the very end. And whenever you do that, you'll notice that in this relationship between the two variables, you change it. It went from an and to an or. And each of the inputs is inverted. So A and B used to not be a not. Now they both have a not on it. And then same thing with the second one. You had an or, now it's an and now both inputs are knotted. Okay? This bar notation is essentially the same thing. So where this apostrophe goes over this parentheses, I just have a bar going over that whole parentheses, okay? And the reason why I like this notation is because it's simpler. You don't have to keep track of parentheses all the time. And because you can think of it as breaking the bar. So I break the bar at the connection. This connection changes from an and to an or, and the bar gets broken up into two separate pieces. So now A and B are both knotted, okay? And then the same thing as what we said over here for this one. It'll make more sense whenever we go through it, but I just wanted to introduce this in case you think this is a lot easier to see. I would like to say before we start, De Morgan's is not the same as going between POS and SOP form. Okay, POS and SOP form give you the same output. It's just different ways of writing it. You're just writing it either as a 1, as in terms of 1, or in terms of 0. De Morgan's flips all your outputs. So any of the zeros you had, they all turn to 1s. Any of the 1s you had, they all turn to 0s. It is not the same thing. And there's actually, I think, 2 example problems at the end of your review that do that. I didn't include it. We can always do it at the end. So we have De Morgan's. I'm going to do it both ways. So we have G is equal to A naught B C, or A B naught C, or A naught B naught C naught. And all of this is going to be De Morgan's, inverted. On the right side, I'm going to write this in bar notation. We have G is equal to A naught B C, or A B naught C, or A naught B naught C naught. And all of this is inverted. So we're going to continue, and we're going to basically break the connection in the largest connections. You want to do, so our largest connections are these OR gates. You want to start, like, if you're to draw the circuit, what is the last gate that you would draw? technically, that's what we're going to do. So we're going to break up the connections there, and we are going to get A naught, oops, that's bar notation, A naught, B, C. Change the relationship, so instead of an or, it's an and. A, B naught, oh, I should have put the or there. Remember that we or each term, then we have A, B naught, C, ORed, and then we have A naught, B naught, C naught, all ORed. So we changed the connection where I highlighted, and then each little term we put a not at the end. I think I said or earlier, my bad. I meant not. For the bar notation, similar thing. I'm going to break it here, and I'm going to break it here. I'm going to do A naught, B, C. All of that has an inversion. We have, I can put parentheses too to separate it a bit. A, B naught, C. All of that is inverted. And A naught, B naught, C naught. All of that is inverted. Okay, we keep going. And now we're going to split up in between each in between each of these for all three of them. So now we're going to have A, and I'm going to put a not because we're technically adding another not on. B not or C not. We have A not or B not, but then we're adding another not, or C not. And then we have A not, oops, oh, or B not, or C not. Now a double inversion, this not, if you invert something, so let's say you had a 0 and you invert it, you get a 1. You invert it again, you go back to a 0. So all these double inversions are just going to cancel. Okay, and this is where, move this up a bit because I'm running out of room. This is where you'll just get, so A double inverted, just A, ORed with B naught, ORed with C naught, ANDed with A naught, or B, or C naught, and then A, or B, or C. Okay, so I'm going to do the same thing over here with this bar notation. This bar notation, I'm basically going to split it up between each of these relationships. I get A double inversion, or B naught, or C naught. I get A naught, or B double naught, or C naught, A double, B double, or C double. And like I said, double inversions cancel. So at the end, I will get the same exact answer, which is A or B, oops, naught, or C naught, and then with A naught, or B, or C naught, and then A or B or C. So those do the same exact thing, different notation. Whichever one looks better for you, oops, sorry. Whichever one is better for you, pick either one. I just feel like the bar notation is a lot easier to see. You don't get caught up in a bunch of parentheses all the time. So let's go on to the next one. Okay, so this one I'll just do the apostrophe notation to save time. So we have H naught is equal to A naught or B naught or C, A or B naught or C naught, A or B or C, and all of this is on a naught. Okay, so I'm going to break it up in these bigger sections. We have A, technically, A naught or B naught or C, and all of this is knotted with the next term and inverted. A or B naught or C naught, and A or B or C. Change the relationship, put an inverter at the end. Next, we're going to do the same thing, but with each of these ors. I clicked the wrong thing. These ors, so we will have A naught naught,
with B naught naught and C naught. I'm going to erase this because we don't need that. Board with A naught, B naught naught, C naught naught. Board with A naught, B naught, C naught. Do not know why I still have parentheses there. Oh, no, it's fine. Okay. And then whenever we simplify that, we just get A, B, C naught, or A naught, B, C, or A naught, B naught, C naught. Any questions on that? Okay. So this one is just another example, but it's saying that you should draw a truth table to see that you worked it correctly. I think we're running a bit low on time, so I'm not going to do it. But essentially, when you draw the truth table, what you should get is, let's say your outputs are 0, 0, 1, 0, 1, 1, 1, 1. All these outputs for your De Morgans should be opposite. So all your zeros turn to ones, all your ones turn to zeros. That's what should happen. And that should be true for any De Morgan's problem you ever do, is that it inverts the output. Because you're essentially putting an inverter gate at the very end of your whole circuit. Okay, next one is conversions. Base conversion between decimal and binary. So in this case, I'm just going to work 183 for both to save time. So we have 183 in decimal and it's telling us to put it into binary using one of the methods learned, division or addition. We're going to do both real quick, just whichever one you prefer. First, division. So you have 183 first. In her review, she did it like 183 divided by 2 is equal to 91 remainder 1. There's another notation where you just do 183, and this is like basically saying divided by 2, which is equal to 91 remainder of 1. This is the way I learned it, where you just keep going. Divide by 2, 45, but then you have a remainder of 1. So whichever way works for you. In this case, it would be 91 divided by 2 is equal to 45, and that does not split evenly, so you have a remainder of 1. So that's the two kind of division notations. I'm going to continue with this one just because that's in her review, but there's another way to do it as well. It means the same thing. So then we have 45 divided by 2. That does not split cleanly, so you get 22 remainder of 1. You have 22 divided by 2. That does split cleanly into 11, so you have a remainder of 0. You have 11 divided by 2, does not split cleanly. You have 5, remainder of 1. 5 divided by 2, you get 2, remainder of 1. And 2 divided by 2, you get 1, remainder of 0. And then 1 divided by 2, you can't do that. You get 0 with a remainder of 1. And whenever I'm going to erase this other division method. Whenever you do this, your final answer, you go backwards. Okay? So you go from 1, 0, 1, 1, 0, 1, 1, 1. And that is your binary value. So that is the...
We have a question
Oh, yeah.
here.
For the truth table outputs, are those considered binary as well? Like the ones and zeros?
Yes.
So like, if you're to read a truth table, do you read it instead of from bottom to up or from left to right?
Truth tables, honestly, doesn't matter the way you do it because truth tables will tell you the inputs. It'll tell you like 0, 0, 0, 0, 0, 1, and then it tells you the outputs. Technically, you could draw a truth table, although most people wouldn't, in a funky order. You could have done 0, 0, 1, 1, 0, 0, and the output.
So say like it's 0, 1, 0, 0. Do you write that like from a line like 0, 1, 0, 0 or like 0, 0, 1, 0?
Typically, you don't use truth tables to convert from decimal to binary, so in that case, it wouldn't be like, they wouldn't like correspond with each other. Truth tables are more so like if inputs are this certain amount, then outputs will be, the output will be like a 1 or a 0.
Truth tables are for functions or equations. This
decimal to binary conversion is strictly just like converting a number to its binary equivalent.
It's like data.
Yeah.
Yeah. So then the addition method. The addition method, you gotta keep in mind placeholders. So what I mean by that is the bit all the way to the right is gonna be your 2 to the 0 bit. You have the 2 to the 1, and it just keeps going up. 2 to the 3, 2 to the 4, and these all have, if you put in a calculator or something, a corresponding decimal value. So 2 to the 0 is the same as 1, 2 to the 1, 2, 4, essentially just multiplying by 2, 8, 16, 32, 2 to the 5. I'm going to have to shift this over more. Then you have 2 to the 6, 64, 2 to the 7, and it just keeps going. It could go on forever. You just have to figure out how many bits you need. So I'm going to rewrite the number we need to find. We need to find 83. So what we're going to do is we're going to find the largest placeholder that we can fit in. So the one after 2 to the 8 is, I'm really bad at mental math, 256. 256. 256 cannot fit into 183. So we cannot have a 256 bit. Otherwise, we'll already be greater than 183. We can't subtract like that. So we're going to get rid of that one. 183, we can fit a 128 in there. So we're going to put 1. So 183 minus 128. I should have brought out my calculator. So we have 183 minus 128. This gives you 55. 64 cannot fit in 55, so we cannot have a bit of that. Next one, we have 32. That can fit, so minus 32. And then we have 23 left. 16 can fit in 23, so then we subtract 16. We get 7. 8 cannot fit in 7. You cannot have an 8-bit. 4 can fit. Minus 4 is 3. Oops, I should have put a 1 there. And then 2 can fit, so we can have a 2-bit. We get a 1, and then we gotta finish off with that 1 so that we get to 0. So that's the other way. And if you look at these numbers, they should be the same. So we have 1, 0, 1, 1, 0, 1, 1, 1. They match. Does that make sense so far? Okay. So now I'm going to kind of move this up. And in your review, I'm just going to get rid of 1 actually. In your review, they do not go from decimal back to binary, so I'm going to do that real quick. So let's say instead you were given this number. You were given the same number that we just calculated. So it's 1, 0, 1, 1, 0, 1, 1, 1. And they're asking, okay, what is it in decimal? So how would you go about this? You will essentially do the opposite of what we just did here. Okay? So we have 1, 0, 1, 1, 0, 1, 1, 1. These are like our little placeholders. So we have 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. Essentially what I wrote over there. So I'm just going to write their decimal values for 8, 16, 32, 64, and 128. And now we're going to look for where is there a 1. Okay, so we have a 1 here, 1 here, 1 here, 1 here, 1 here, 1 here. So we're going to say, okay, that 1 first, all the way to the left, 1 bit is equal to 128. So we have 128, skip to 0. Next one is 32, so plus 32, then plus 16, plus 4, plus 2, plus 1. And if you add all of that up, you should get 83 again. So that's how you go from binary to decimal. Okay. So next, we have hex conversion. Convert both numbers to hex. We're just going to do one. The way you do it is the same. So for hex, you can either go straight from decimal to hex or from binary to hex. So I'm going to do both ways. So binary to hex is definitely the easier one. So let's do that one first. So we calculated our binary number earlier. We had 1, 0, 1, 1, and 0, 1, 1, 1. Hex is our base 16. Basically what this means is we have 16 numbers we can represent. we can represent 0 to 15. Okay? If you have base 16, it's 4 bits. So if you have a 1 in all of them, this is equal to 15. Okay? And if you have 0 in all of them, it's equal to 0. Okay? So we have 4 placeholders for hex. Okay? Which means we're going to group up our binary numbers into 4. So I've separated them here into 4 bits per number of our hex. And we're going to say, how much is that equal to? So let's look at this left one. And whenever we convert this, how much is this equal to? Well, we have, we'll put this place essentially a 1, a 2, a 4, and an 8, right? Keeping in mind those placeholders. So we have an 8 plus a 2 plus a 1. This is equal to 11. And now we come to this problem of 2 digits. So if I was to give you a number that was like, let's say 11, 2, and then if I was to give you 112, or like 112, in hexadecimal, we talk about places similar to we do in binary, right? So how do I know that these two is one placeholder and then these two are 3 different digits? Like in this case, we should come out with two digits, okay? Because we have 2 groups of 4. So that's 2 hex digits. But what if I had like 0001, 0001, and then 0010? That's 3 places, and this one would be equal to 1 in hex 2. So how do we differentiate between these 2 things we just did? They look exactly the same. Okay, let's pretend like this eventually went to a 2. Okay, we're not there yet. That is why we eventually start, instead of saying, okay, 2 digits, we're going to represent it as a letter. Okay, so that it stays as 1 digit, and we know that it's 1 placeholder and not 2 different ones. So whenever we get to this problem, we have to represent 10, 11, 12, 13, 14, and 15 in hex, right? Because I said that that's the base. So we're going to start doing letters. Once you get to 2 digits, you start with A, you go to B, C, D, E, and F. Does that kind of make sense so far? Yeah. Okay, so 11 corresponds with B. So this hex number is actually B. It represents 11 in decimal. This next one, we're going to do the similar thing where we have 8, 4, 2, and 1. We have 4 plus 2 plus 1. This is equal to 7. And so 7, we don't have to worry about 2 digits. We can just write it as 7. So for our hexadecimal number, this binary number is going to turn to B7. Does that make sense? Okay. I said that you can go from binary to hex, and you can also do decimal to hex. Binary to hex is definitely like a more intuitive because you kind of group it in 4, but it is possible to go from decimal to hex. This way is a lot similar to your division method whenever you go from decimal to binary, where you divide by 2. But instead of dividing by 2, because we're not in base 2 like binary is, we're dividing by 16. It's a lot less intuitive, so I would recommend doing the binary to hex way, but it is possible to do it the other way. So like if we said that this binary number that we calculated earlier was 183. So if we were just given 183 and we want to skip the whole binary stage, what we would do is we would do divided by 16. Okay, so when you do 183 divided by 16, you get 11 and you get a remainder of 7. So keep in mind, earlier we only had a remainder of 1 or 0. That's because we were working in binary. We can only represent it with 0 and 1. But in base 16, we can represent 0 to 15. Okay? So, and then you would keep doing that. You would keep doing divided by 16, and find your remainder. It's a lot harder than doing just the binary conversion way, because binary conversion, you either have remainder 1 or 0. This one, you have to be like, okay, I get 11 out, 11 times 16, like 183 minus that, how much is the remainder? It's kind of more steps. So whichever way you want, if you really like the division method and you really don't like converting to binary, this is another option. I won't go all the way through it. Actually, I can. It's like no steps at all. So next is 11. 11 divided by 16. You can't do that. 16 doesn't go in, so you get 0. And you get a remainder of 11, which we said was same as b. And remember, when you do division method, you got to go backwards, so you get b7. Another way. Pick whichever one you like more. You will not be asked to do a certain way just to find the answer. Any questions? Okay. So now we have convert each of the decimal numbers to decimal from hex. Decimal and binary from hex, sorry. Okay, so now we have, I'm just gonna do like the top one because low on time. But for the top one, we have E. So I'm gonna do this one is gonna go to binary. So this is gonna be 2 binary because that one's a little bit easier. And so we have E, we have 6, C, and 8. Remember, each of these digits is 4 bits. I should have wrote that better. I'll move in later. So we have E. I'll put it above E. Move 8. Move the C. Move the 6. So each one has 4 bits that have to represent it. E. I'm going to write on the side again. We have A, B, C, D, 10, 11, 12, 13, 14, going up to 15. So then we have E and F. These are our letters that we use to represent 2 digits. So E, it has to be 14. So we are going to make 14 in binary, in 4 bits. So we have 8, 4, 2, and 1. Notice we're just talking about like each digit is 4 bits. So I'm not going to count like 1, 2, 4, 8, 16, 32. No, it's just 4 bits to 1 digit, not all of it. So you don't have to look at it all the way like that. So when you do this, 8 fits in once, and then 4 fits in, that makes it 12, 14, and we don't need a 1. Next one is 6, so we're going to have a 4 and a 2. I'm doing this kind of fast. If you are confused, please let me know. C will go to 12, so we have an 8 and a 4, and we don't need any others. And 8, we just have the 8-bit. And that is our full binary number out of hex, out of the hex number. Yes, keep in mind that if you do have, I forgot to say this earlier, but if you're going from, from binary to hex, let's say you have kind of a weird number, so you have like 0001, and then let's say you're only given like 1 in front of that. And you're like, well, I need 4 bits to represent each hexadecimal number. This one only gives me 1. Everything in front of it, the other 3 digits, are all zeros. Because if you put a 0 in front, it doesn't change the binary number, but it gives you those other zeros to tell you like what the number. It gives you all 4 bits to work with. So you might have something like that. Next, we have 2 decimal from hex. So if you are given, this is going to be similar to, so these are my things, and I have placeholders. So similar to binary, we talked about there being placeholders of like 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. Now we're in base 16. So now we have 16 to the 0, 16 to the 1, 16 to the 2, and 16 to the 3. Earlier, what we would do is we would just add like 8, 4, 2, 1. But why would we just add them? Because we're multiplying it by 1, so it doesn't really change anything. So technically, if we were to change this to decimal, it would just be 1 times 8, and then plus like 0, plus 0, plus 0, right? Here, we actually have values other than 1. So E corresponds to 14. So actually what we would do is we would do 14 times 16 to the 3 plus, now next we have a 6, 6 times 16 squared. Board with C goes to 12, 12 times 16 to the 1, and then we have 8, and then 16 to the 0, which that's just 1. And you add that all up, and when you do, you should get a really, really large number. So I'm not going to work that out, but you should get that. But that's the process you go through. Very similar to binary, except now you just have a base of 16. Any questions? You good? Okay. Oh, right. I added an extra slide in because this was a last-minute decision, but this is for octal. So let's say we have 7, 2, 5, 1, 4 to the 8, which is octal. Octal is, like the name suggests, base 8, which means we will represent 0 to 7, 8 different digits. For 0 to 7, you only need 3 bits because 1, 1, 1, and 3 bits is 7. Okay, so that's all you need. The highest value is 7. So that means we have 3 bits to represent our 7, 3 bits to represent our 2, 3 bits to represent our 5, 3 bits to represent our 1, and 3 bits to represent our 4. Okay? So when you do this, 7, this is the, oops, not 8. This is the 4 to 1 place. So we need a 4, a 2, and a 1. We just need the 2-bit here. We need the 4 and the 1-bit, just the 1-bit, and then the 4-bit, and that's it. So similar to hex, except now you only have 3 places because it's an octal. And that would be your binary equivalent. And for just decimal straight to base 8, it would be a similar thing where you divide by 8 and then whatever your remainder is. Same process, just dividing by a different base. Yes. Next one I'm going to kind of speed through because it's also very similar format. BCD, you're doing the same exact thing where you change each number into its own set of bits. So we're going to look at the largest number, 8. How many bits do we need to make 8? Well, we need 4 bits because that's 1, 2, 4, and 8, right? So that means all of these are going to have 4 bits. You represent 1 with just that on the right. 8 is this bit, all the others 0, and 3 are these 2. So very similar to hex, octal, and all those, except you're just converting the decimal into it based on how many bits you need. You'll only need 4 bits actually ever because the most you can represent like in a BCD display is 0 to 9, and you can represent 9 with 4 bits. So should always be 4 bits actually. Now that I think about it. Binary addition. Okay, so with binary addition, it's similar to kind of when you just add in math class, in which you start with the right, you add, you carry over a digit, except this time you don't have a max of 10. Because when you're in decimal, you know, you do like 9 plus 1, oh, that's 10, carry over a 1, right? In this case, we can only represent with zeros or ones. So if you have, let's say, like 2 ones being added, you're going to get a 0 and you're going to carry a 1 because you can't represent a 2. You got to move the 1 over. Yes. And then I said about adding 3 ones. What if you did like that? Well, you would have 1 plus 1, 0, carry a 1. Now you have 3 ones. Well, 2 of those would go to the carry, and 1 of those would stay. So you would have that. Does that kind of make sense? Because here we have 2, so it goes like 0 and we carry over the 1. Here, like these 2 will turn into this carry, and you just have this 1 left over, which goes down below. Okay, so we're going to add this. I'm just going to give you the binary values. We're not going to convert it just for the sake of time. So we're going to have 0, 0, 1, 0, 1, 1, 0, 1, 1, 1. 0, 0, 0, 1, 0, 0, 1, 1, 1, 1. Okay, I'm going to do this in different colors so you can see the carries. We're going to start all the way on the right. 1 plus 1, 0, but we carry a 1. Here's, like I said, that 2 of these will go over to make another carry of 1. and the other one is left to the bottom. Next, we have the same exact thing, a 1 and a carry 1. 1 plus 0 plus 1, the two ones will turn into a carry. Once again, we have two ones, turn into a carry. Two ones, turn into a carry. Two ones again, turn into a carry, and so forth. Now we just have a 1, 0, 0, so that'll turn into a 1, and then we have a 0. Did I go too fast, or does it make sense to everybody? Yeah? Okay, so that is how you do binary addition, essentially. It's just that kind of step. If you do binary addition and I'm going to briefly touch on this, and you get like a 1 all the way out here, that's called an overflow. It means that you do not have enough bits to represent your answer completely, in which you would have to add like more bits above in order to make it work out. I'm not going to go over overflow too much because that'd be a lot of talking, but at the end we can always go through it. 2's complement. So I put 2's complement next because we're going to have to do subtraction. In order to do subtraction, we can't just subtract binary numbers. We have to represent the second number as a negative number, unfortunately. So 2's complement is a two-step rule. We have, I put the whole chart here. We're just going to work through some examples. So 2's complement, basically what it is in the front there is a sign bit. Okay, if the first bit is a 0, this means it is a positive number. If it is a 1, it's a negative number. Because otherwise we have no way of finding out. It all looks the same. It's all 0 and 1s, right? You will not see a number and have to figure out if it's 2's complement. You will be told it's 2's complement, or you will like solve the 2's complement yourself, because you can't tell otherwise from up here or something like that. So let's say we want to represent like -3. So we're going to write 3 in binary first. So we have 1, 1, 0. And whenever you do 2's complement, you always want to have leading bits. So we're going to add more zeros in the front in order to make it so that we know for sure that this is a positive number. Okay? Because we could have said, oh, 7, we have 3 bits, and this looks negative in 2's complement. But what we want to do is we want to be like, okay, we're starting off with a positive 7, so we want to add some leading zeros. Okay? The next step is to invert everything. So all your zeros are going to turn to 1s, 1s turn to zeros. We have 1, 1, 1, 0, 0. And then we are going to add a bit. This is just something you have to memorize. I don't have a way for you to memorize it easy. Just invert, add 1. When you add 1, you get a 1, carry of 0, and then the rest stays the same. And if we look, this matches what is on our chart. Okay? That's kind of the step process about that. And it's leading with 1s, which means it's a negative number since we're in 2's complement. Subtraction. Subtraction is kind of the same way, except transform the second number into negative and then add as usual. Yes. In this case, your carry-out bit you will have to discard, and if you're ever confused about that, just at the end, change your answer into decimal, and if it doesn't get you the right answer, then it's probably because of this little dude right here. So keep in mind you're working 2's complement, so if your answer is negative, and you know it's going to be negative, which I have an example later, you'll have to do 2's complement to the answer in order to find out the magnitude of the answer, like what the positive of the answer is. So like if I was supposed to get a -3, whatever my binary number is, whatever, I will have to do 2's complement in order to get decimal value 3. And we have an example later, and I'll do that. So subtract this. I'm going to put the numbers again. These are the same numbers as before. And then we come into the problem of, oh, this second number is negative. We got to convert it. Okay? So the original of 79 is, so this is 79 positive, okay, which you do on your own. So we have to invert this first, 0, 1, 1, 0, 0, 0, 0. I forgot to add my leading zeros, so I'm going to add some now. I'm gonna add like 3. Okay. Remember, you always have to add leading zeros, because otherwise this looks like a negative number. Okay, we first want to make sure we have leading zeros to say it's positive at first. We're going to 2's complement it to negative. Okay?
You have a question? How can you say for the leading zeros, does that have to be 3?
It doesn't have to be 3. I would suggest putting more than you think, because if you have too little, it will change your answer. Yeah. I would say 3 is a safe number, because I've done it with 2 and I've gotten the wrong answer, so that's just that. And then we're going to add 1. Okay, so that's what I get. I'm now going to put it here. And we're going to add like normal. Okay, so we have this. I should change the color so you can see. 0, carry 1, 0, carry 1, 0, 1, just 1, with a carry of 0, 0 to 1. I'm moving kind of fast. If you ever are confused, please let me know. Just running slightly low on time. And this is our carry bit, remember? And so with this, you have to drop your carry bit. So we're going to get rid of that. We are left with this. So now let's check if we're correct. Okay. So we have leading zeros, so we know we are in the positive range. Okay. So we don't have to 2's complement again. We can just solve this. So this is the 1's place, 2's place, 4, 8, 16, 32, and 64. So we should have 64 plus 32 plus 8. And this should get us our complete answer, which is 104. And I'm going 183 minus 79 is 104. So we got that correct. And that is how you check your answer, is you put it back to decimal. Any questions? No? Okay. So I put in, this is the last slide, by the way. I put in an example where you end up with a negative number as an answer, so you can see what I'm talking about. So this is, I put pretty simple numbers. So 2, I'm going to put them in 5 bits. So 2, I have 0, 0, 0, and then 0, 1, 0. So that's 2 in binary using 5 bits. We got to change our 5. So 5 normally is 0, 1, 0, F random 0. 5 bits is that. 2's complement it, invert everything. 1, 1, 0, 1, 0. And add a 1, 1, 1, 0, 1, 1. This is negative 5. So whenever we add that in, oh, not enough bits again. I missed. No, we're fine. I think I just added too many bits here. There you go. So then we have 1, 1, 0, 1, 1. Add it. Add like normally. We have 1, carry 0, 0, carry 1, 1, carry 0, 1, carry 0, and 1. That is what we are given. So there's no carry out bit in this case. There's no bit like out here. And we started with 5 bits for everything. We end with 5 bits, so there's nothing to drop. Carry out bit is like an extra bit. You didn't start with that many bits. You got an extra one in the process. Okay? So now we have this, and we notice that this is a negative number because we are working in 2's complement. So in order to figure out what this is in decimal, you have to convert it first. If you convert it now, you will get a number too big, something that is not 2 minus 5. Okay? So we have 1, 1, 1, 0, 1. We're going to invert it, 0, 0, 0, 1, 0. Add 1. We get 0, 0, 0, 1, 1. What is this in decimal? This is the same as 2 plus 1, which is 3. So since we did 2's complement, we should remember, oh, by the decimal equivalent is 3, but we did 2's complement, so actually this is negative 3, because we had to do 2's complement to get this answer, which is 2 minus 5 is negative 3, so our answers match what should have happened. So 2's complement is very weird in that you have to look at these leading bits, and you have to see if it's negative or positive at the end. And if you don't look at that, then just on your calculator, do the regular decimal and see if your answer should be negative or positive. If it should be negative, then you have to do the 2's complement at the end to find out what your answer actually is.
So you're saying 0, 0, 1, 1 is -3, or 1, 1, 1, 0, 1 is -3?
So this is -3 in 2's complement. This is just the process of finding what it is in decimal, because we can't use a 2's complement number and just immediately convert it into decimal. We have to like change it back to the way that we originally know. So this is just trying to basically find the magnitude of what it is, basically what it is. And that's why I said you have to realize that, oh, we did 2's complement, so this actually should be a negative number at the end. Yeah. Any questions? Yeah. So that is all we have. For this room, we're going to be like out of time essentially. Varsha and I will stay behind a bit to ask if you guys have any more questions. We also have a tutoring channel which you can message in. If nobody's in the IEEE Discord, please come to us and we can get you in there. Basically, it's a tutoring channel where you can send a message and be like, hey, I have a question on this class. Is it possible I could get help? And we have many tutors that will be there to help you with your either lab or homework or anything like that. Yeah, so that's it for now. Thank you.